So Dev, you can share a screen.
Yep.
Just you can turn off the video. That might be, hopefully, that might make it better.
Is my screen there?
Yes.
Perfect. We can go off this way. Uh, huh, much better. So, hello everyone. This is me, Dave, and I'll be off presenting this set of whatever I've prepared, I've worked on, and uh, to begin with, what better than just to have a small idea, a small intrinsic insight into what are LLMs, why we will be using it, and like I was proposed many questions that over time the answer would come up to me. Why I'm using a particular architecture, how I'm able to like why I'm choosing a particular pipeline and not the other, since there are like multiple open source and closed source LLMs, multiple even API keys there for fine tuning. So why did I choose the one I chose, and how it is factually and numerically better, and like it's better than the other architectures that I refuse to progress with. So once again, understanding large language models. On my left you see the entire architecture of a transformer, the standard architecture proposed in 2017, I guess. Attention is all you need. Google standalone, the major paper, and there came the advent of LLMs, that essentially is an AI much better than the pre-existing RNNs because of certain cases, because of certain principles that LLMs use. That is the standalone encoder decoder architecture that comes from the transformers itself, built on self transformer architecture. Over time, like once when I'll be going into the complete delicacies of into how every single aspect of this entire architecture works, I think it will be much better when we'll be going inside it. So that sums up to what LLMs are. Trained on extensive data sets, perform tasks like text generation, text sentiment analysis, and even retrieval of text, like retrieval generation text, retrieving text from important documents. All of these tasks, these perform much better than the pre-existing RNNs, the recurrent neural networks. How they do it, what's their architecture, that follows up to our next slide. The key models, once I'll just make a special note of this: BioBERT, Roberta, and AristoBERT. This is something I'll come extensively in the second half of my presentation. But before that, let's just understand what is LLMs and why we are choosing it. A major question: the timeline. What uh, allows us to see, what allows us to see, and what allows us to understand how LLMs work. If you see the diagram on my right, like if I may zoom on it, these are the performance of, this is a complete pictorial representation of the performance of LLMs over time from 2022 to even like 23 on the USMLE dataset, a dataset that comprises of biomedical question answering, and this is an entire pictorial representation of all the 4 different types by which LLMs can be tested, be it prompting, fine tuning, pre-training, as well as human expert. That is when a human sits there in order to prompt and fine tune the model consistently, consecutively, like deploying an RAG, but that's something we will again come up in the second half. Over here, if you can just focus on this, the highest achievable accuracy has been gained by GPT-4 MedPrompt, and this is a closed sourced LLM. It has not been open sourced, and it contains about 170 billion parameters. The highest available open source that has been achieved is by Llama 2, Meditron, and also, and this comes in pre-training. A similar question that was asked to me was the difference between pre-training and the difference between pre-training, fine-tuning, and prompting. A complete segment which I'll individually discuss in the upcoming parts. This portion, BioBERT. What BioBERT is, it came in 2019 only on biomedical tasks. and it's better than GPT-3 and even BERT, which came in 2016, BERT in 2016, and it retains around 97% of that information at around 60% of that size. So that's a complete, a great advantage in itself. If we can focus on this architecture, this one actually shows us, I'll open this to what this shows. It's much more beautiful when we understand. Okay, this one actually shows the open source models are actually represented by solid squares, whereas the closed source models are actually represented by these hollow squares, which brings us to over here, when there are the three types of architecture that we saw just in our previous slide. The transformer architecture that consists of both the encoder and the decoder architecture. Now LLMs can be built on either of the combinations of this. It can have only an encoder architecture, it can have an encoder decoder architecture like the standard transformer architecture, or an only decoder architecture. Over time, this is the performance of all of these LLMs and their respective architectures. As of now, GPT-4 has been the decoder only architecture, the boss of all LLMs, and for only encoder decoder architecture we have GLMs, FLAN-T5, and there is this recent announcement of Llama as well. If you have read or if you have been in the news, there's Llama, and NVIDIA also used, NVIDIA also open sourced its NVIDIA Tron. So that's also 7 billion parameters, and that's one of the best open source encoder decoder architecture presentations, encoder decoder LLMs out like right now. This is again something we will come back again when we will be understanding how every LLM works, or how for why every LLM works and where every LLM works. So there are these three essential questions that we will be answering throughout our presentation. One, how LLMs work. That's our first question. And how does this entire text generation or text or information retrieval, or even sentiment analysis, or even like our major project motive, like the drug target discovery, how these things work. Second, why second, I'll just come back once again. It's again like how, why, and where. Okay. Am I still audible? I will just have a quick check.
Yeah, I can hear you.
Okay, thank you, sir. Moving on to the encoder architecture of these LLMs, the standard one that we initially saw from here. If we are allowed to zoom over here, the encoder architecture contains three important segments. One is the input embedding. How does this come across? What is positional encoding? And what is this plus sign? Following which, what is this entire layer that forms in between? Let's go all of this one by one. An encoder architecture, once a complete sentence is generated, we have a corpus of a complete sentence. Each token, each identifiable token of that entire sentence is converted into a dense vector. This vector essentially has the dimension of, it has a varying dimension depending upon which LLM and which vector you are using, but essentially it has a dimension of 1 cross 768. This vector is known as the input embedding. One, if you can see right over here, this one. I drink things, know when we will play out a random sequence of words, and which are then converted into a vector like this. Now, what makes LLMs different than and more faster, more suitable, and more easily usable over a large corpus of data rather than RNNs? When we are from our existing knowledge of recurrent neural networks, we know that when it parses information, it essentially takes the entire sentence, and one by one, every single token or every single word is parsed through the RNN, and a new word and a new then the ultimate proceedings work. But in LLMs, things are a little different. All the words are parallelly fed into the matrix, and like if there's this one sentence called "I am a good boy," in the existing structure of RNNs, I goes first into the neural network, then am goes in, then goes in, and good and boy. But in LLMs, all of these are parallelly fed into the matrix. So how does the LLM understand which position is occupied by which word? How does it understand that good occupies the index 4 and boy occupies the index 5? This is through positional encoding. In positional encoding, every single token is given a single vector element depending upon its odd position or even position on the formula provided over here. For even position, for example, in this sentence itself, I drink things no, and a random sequence of words, I know, but I drink things no. The first one is the oddth position, and position of odd is given this cosine of position divided by 10,000 to the power 2i divided by dimension of the model. This becomes very important as we dive deeper into the architecture of encoder and why things work. Like the second question, if we have in mind, the first one was how things work, and the second one was why things work. And simultaneously, we will have our even position calculations as well, the positional encoding of that particular element. So if we just hover on this matrix once again, we will have that all of the 6 words have their independent input embeddings fed into this matrix, and simultaneously all of them have their position embeddings as well fed into another matrix. The LLM, this is the part where these two matrices are simply added. I'll mention this one once again. This is a sheer case of concatenation of the positional encodings of the words of the tokens that are fed into the matrix added to the corresponding word vector. They are added, and this completes the initial part before we enter even into the encoder of the LLM. The first half ends over here, like not the first half, I mean the first tiniest portion of LLMs before we enter into the encoder architecture, like how positional encodings work, the formula for each and every item, each and every element in the matrix, how they are concatenated with the word embeddings produced by the this entire embedding calculation, and finally coming down into feeding into the architecture. Following this, we have a quite interesting part. Like if we can again hover to the initial page of our architecture, this is where we are right now. We completed our input embeddings and positional encodings, and now we are heading on into this block, the first black box of our day, the encoder architecture, the what goes inside multi-head attention. What is attention mechanism, and what are the 3 different types of it? Let's check out that once. Attention mechanism essentially is giving each processed token a specific value that announces its probability of occurrence to the upcoming segments of the model. There are essentially 3 parts of attention mechanisms: single head attention, multi-head attention, and cross-modal attention. The last one has been proven and explainable to be much better one, and I want everyone's I just want attention everyone's attention to come on this CMA part, because this is one where we will be this is a tiny portion that will add a major factor to our final project, like when we will be adding in CMA to our final layers in order to boost our accuracy by a huge amount. Coming to the self explanation of what is SHA and MHA. Single head attention, I have tried to explain it in very concise pattern, maybe focuses on single aspect of the input sequence. I'll again come back to the initial sentence once again. I am a good boy, so I am a good guy. So every single token is attached an attention. How does this attention work? This essentially comes by 3 vectors: the query, the query, key, and the value. How does these 3 vectors come? The attention matrix, that is the entire matrix passed on to the input over here. This final matrix that is passed on to the entire architecture, this is taken as the initial matrix, the initial input embedding matrix to the encoder architecture. Over here, we have 3 weight vectors: W0, W1, and W2. On just doing a dot product of this input embedding matrix with W0, we find the query Q. With W1, we find key, and with W2, we find the value vectors. Post that, we compute the attention scores by taking a dot product of Q and key, Q and K, and applying a softmax function. this becomes our standard algorithm, or the standard essence, the standard way by which we will be computing SHA, the entire output. It starts from having a softmax function of Q into K. If we can focus over here, Q into K transpose whole divided by root over of dk. Q stands for the query that we found by multiplying, by just doing a simple dot product of the input vector, the input embedding matrix, a dot product with the weight 0, vector. We found Q, and simultaneously with weight 1 we found key, and finally we will find V, the value matrix as well. dk is the dimension of the key that we have over here. What we have over here is in the single head attention, and we finally come to the producing a single attention output vector that combines information from different positions in the sequence. If we just focus on this algorithm, this small flowchart that's over here, Q and K taken as a matrix multiplication, a simple dot product, K transpose actually, then again scaled, again matrix optimized, matrix, this is the optimization or the normalization factor, that is the Q dot product of K transpose is divided by root over of dimension of the key matrix, then applied a softmax function over this, and here was the value vector that we found by multiplying the input embedding matrix with the last of the weight vector W2. These two are again cross multiplied, and finally we get this last matrix multiplication output. This concludes our single head attention, like the entire topic. Now, if we can just combine this architecture, this single head architecture, into multiple such, like we can just duplicate this one small flowchart into multiple such flowcharts, and then finally choose the best flowchart out of those. That's essentially what multi-head attention is for you. Multi-head attention, like I have tried to write it in very short, instead of one set of Q, K and V vectors, multiple sets are used, and each head performs the attention calculation independently. I would like everyone's attention to be focused on this one, because independently is kind of the keyword over here. Every single SHA is independent of its action, and when each of those are merged, like concatenation of linear transformation, to produce this MHA output. And over here, if you can just zoom over here, this is actually the MHA output, where it contains n heads. These every single flowchart consists of the head, and finally we get the multi-head attention, and we just concatenate all of these features, we have our multi-head attention. For cross-modal attention, I'll be referring to a paper that I found, that I've read online, and I'll be going to that, but that again comes in the second half, when I'll be trying to make, boost our accuracy of our proposed architecture. So I'll just skip this small part about what is cross-modal attention. If you can see, again I've pasted in the flowchart right over here what is scaled dot product attention and multi-head self attention. Like, this flowchart is actually quite beautiful right in itself. Scale dot product attention, the same flowchart that I explained to you, this same exact flowchart duplicated for multiple times, and then all of the results are concatenated and then passed to a linear transformation function. This forms the multi-head attention architecture. This becomes very much beautiful because throughout our encoder architecture, like SHA was depleted long back, and ever since MHA has been like bossing around throughout this architecture. I'll just skip this small part, and I'll make sure I come back once again to it in order to make things, in order to actually boost our accuracy levels. I'll tell why this, I found it better than the existing ones. So this is a very nice visual representation of actually what I found online. Adding and normalizing every single part, and adding and normalizing essentially means every single output or every single vector that we are receiving, we normalize it in the required frame that we need. We complete that, and finally, if you can locus over here, every single value that goes again into multi-head attention. Now, how things work and what we did complete right now. We completed this half of the encoder architecture. We saw what multi-head attention is, and feed-forward network is nothing but essentially transferring that through a linear transformation function into the next level. And there are such multiple encoders attached before we transfer this entire idea into the decoder network. multiple sequentially encoded networks are arranged, and then this entire value matrix, that's finally the encoded value matrix that's formed, is transferred into the decoder. That goes in there, and let's see what we have over here. Okay, what we have again over here is the decoder network. Am I like, do I have any questions or anything, or do I continue with the decoder architecture as well? Hello?
Go ahead.
Okay,
Yeah,
thank
go
you so
ahead.
much. We go
Keep
over to the
continuing.
decoder
Yeah.
architecture, this entire part, and I'll just give a small brief of what there lies. We understood what multi-head attention is. Now we'll go a little step ahead into what's masked multi-head attention, and then adding and normalizing every single feature that we will be receiving from that matrix. And then again adding and normalizing, feed forward, and finally passing it through a linear and a softmax function to get the final output probabilities of every single token parsed into the LLM. Decoder architecture. What's MMHA actually? Masked multi-head attention. We understood what is query, we understood what is key, and we understood what is value. For every single of this, we apply a small mask to prevent that addition into future positions. I would love to go into the like the exact mathematics or the exact linear algebra of this, but that would essentially consume a lot more of time, and I actually would deviate the course of the presentation. So I have just kept it in smaller terms, that it contains all the it performs multi-head attention and then concatenates them. It's like a concatenation of MHA, multi-head attention. Over every individual matrix obtained, it performs MHA over that and then concatenates. Over here, if you can see head 1, Q1 equals to K1 equal to V1 is the input matrix. We find the QKT, W1 is the softmax of A1, that's A1 divided by root over of DK. And over here, if you can see, once when we put the masking essentially means taking any random elements present in that vector and like bring it down all to 0, so that there's this mask or a single iteration of the, or a single like cloth that actually acts as a garb over that particular element. Then we again go to O1 is equal to W1 dot product of V1, and every of these heads are then concatenated. Apply learnable linear transformation, and it's a masked multi-head attention with 2 heads. Now we come to this second ontology, the second description of what LLMs are. Like this, we have this entire segment called pre-training of LLMs. That's essentially using language modeling. We have masked language modeling, then we have next sentence prediction. The second half after masked multi-head attention is the next sentence or the next word prediction. For example, if I am writing, we have all have read that same that simple email when we write in our Gmail boxes. We are writing a particular mail, and then the email prompt that comes up with a new the next predicted word. So how does that come in, and the consecutive maths just behind that. Applies a small softmax layer to convert the scores into probabilities for every single word that the model has learned right now, and then the word with the highest probability is predicted out. This is like very over the crim explanation of what is next word prediction, but again, like over time we will be again coming it into autoregressive and auto-encoded language modeling as well. So that's when we will learn in much more detail about how pre-training occurs and how masked multi-head attention and next word prediction are much more important than the credit we offer to them. This actually essentially completes our decoder architecture, and if we again come over here, we have the same adding and normalization layer posed by the feed forward network. We have the MMHA, the multi-head attention, and the feed forward that essentially predicts the next word. Over here, the black box completes itself, and after this we have an idea or a probability score of which word or which sentence or which token to generate next, which is then parsed off to the softmax layer to get the final probability. Throughout my time when I was working, when I was researching, when I was trying to figure out things, I found this one question offered to me, that since we are working with biomedical data, since we are completely immersing ourselves into biomedical data with our entire project title being drug target discovery, that is We need to read a lot of papers. We need our LLM, our chosen LLM, to read a lot of papers, to understand the intricacies of those papers, and finally have its own predictive abilities for the queries that will be passed on by the user. For example, we always wanted to have one multimodal LLM that could parse in all of your queries and give in the absolute specific answer that could be used either by scientists doing drug discoveries, or researchers, or genetic researchers, and lot more. Why? Then this question always occurs to me. This question I was asked as well: which one to use? As I just showed in my previous slides, there have been multiple LLMs being brought out by multiple companies, be it Perplexity, be it Anthropic, be it OpenAI, be it Google, Meta. Everyone has their own LLMs, and every single LLM has its own particular use case. We can't, essentially it's like comparing apples and oranges, to be very frank and honest, but still every LLM has its specific use case, and I'm like trying to focus on just 2 LLMs, and I'll just try to compare of their architecture and say why for specific information retrieval from specific documents there always lies a trade-off between these two, BERT and Llama. BERT essentially came out in 2016, Google bought it, and Llama bought by Meta in quite recently. It was in 2019 or something, I'm not sure of the date. But BERT follows the transformer, the standard transformer architecture, also again explained by the same 2017 paper, and Llama focuses on a self-attention architecture. If you can see over here, self-attention grouped multi-query attention with KV cache. All of these 3 vectors, the query, key, and value vector that we just understood, by multiplying the input embeddings with their respective weight vectors, are parallelly passed into a SHA, then normalized and feed forward, and finally again given into a normalization, and that's that final output. And this one is the transformers architecture. So why is this single architecture better or worse than like I can never say better or worse, but for our specific use case, which is like more usable, or which offers a better understanding or a better useful case? I chose BERT, and my reasons are right over here. BERT has established performance and multiple more citations than Llama. This might also be because BERT is relatively older and researchers have had their time understanding the architecture and the entire depiction of why BERT works, of fine-tuning BERT and making specific models of BERT, be it BERT for common sense question answers, or be it Roberta BERT, be it AristoBERT, and for like common sense question answers, or day-to-day or scientific question answers, or even biomedical question answers. We have everything. But for Llama, no such existing, I wouldn't say no such, but less such existing work has been done. Robust fine-tuning, BERT offers this entire fine-tuning architecture for domain-specific tasks, and a stronger community support, owing to be like Google has one of the highest engineers, of course, and has been cited by much more people. Llama, on the other hand, is apparently computationally efficient, and it's much better for resource constrained environments, only because all of these 3 vectors are parsed in parallelly to the single head attention model. Over here we were using multi-head attention, and every single like of these vectors Q, K, and V were parsed in one by one, and then there was the softmax layer, then there was this O value formation, and then multiple such O values were concatenated to form the masked multi-head attention, which takes much more time and much more computation power, not available on our local laptops, of course. Llama solves that problem, takes everything in at parallelly, resource constraint, for resource constraint it's damn good, and it can also handle large data sets. But why we face difficulties? Because existing Llama research has not been fine-tuned over specific data sets pertaining to our corpus. For example, if I need a model specifically only for biomedical data set, I won't have a Llama model fine-tuned to that. I am essentially required to do that on my own, and that would require a lot of computation, lot of computational power, lot of architecture handling, and a lot more. On the other hand, BERT has actually, there was actually a research by Korea, University of Korea, and they proposed BioBERT, which is something again I'll be proposing just in the next slide itself. BioBERT is essentially trained on 18 billion tokens, 4.5 from PubMed and around 13.5 from PMC. 18 billion tokens, and has been trained and fine-tuned on that specific data set, which makes it much more easier for us as users or as second generation developers to clone that, fine tune it on more of a smaller subset of those papers, and have our like constrained specific results. We have less SWs because Llama has lesser community support, which is quite obvious. Following this, we actually enter into BioBERT. What is BioBERT? How this thing works over here. Throughout the presentation, like I failed to mention this one thing, that what's BERT actually? What does BERT stand for? So BERT actually stands for bidirectional encoder representation from transformers. And why bidirectional? That this term comes from its pre-training portions of BERT. When BERT pre-trains, there are actually two different ways of pre-training an LLM. It's either auto-regressive encoding or auto-regressive encoder or auto-encoder or auto-encoder language modeling. The two different types of language modeling for pre-training a transformer. BERT is the better one. It like reads a sentence both from left to right and right to left parallelly before performing any of its tasks, be it NER, named entity recognition, relationship extraction, dependency parsing, question answering, or even answering specific questions pertaining to the dataset that is fed on to that particular model. BioBERT on my left has this entire pre-training. Like if I am allowed to zoom into it, PubMed has around 4.5 billion words. I want to make sure of this, that this is only the free version of PubMed that BioBERT has been trained upon. PubMed, like I and Gyan sir were calculating the other day, PubMed has around 60,000 articles, and every article's around like if every article contains even around like just a basic amount of 3,000 words, it exceeds a lot than 4.5 billion that's over here. So we came to the conclusion that BioBERT was only trained on the free articles that are freely accessible to the user. That's the pre-training corpora. And if we can just zoom again into a little bit here, that's the weight initialization of from these corpus. And again we have our pre-trained BioBERT with the biomedical corpora, and fine-tuning over every specific task that we want. For example, if you want a particular gene-gene interaction, if you want a protein diseases interaction, or even if you want a gene to disease interaction, BERT can be fine-tuned on all of these datasets, provided we have a subset of data that's not entirely different from biomedical, but can be used to fine-tune our entire model. Then we have fine-tuning and the entire. So essentially what we come to the conclusion is BioBERT, a model fine-tuned for biomedical tasks, can perform tasks much better. What tasks it can perform? Like entity recognition, question answering, given the relationships between any two
Dave,
genes. Yes, sir.
Dave, in this table, it shows the gene disease relation.
Yep, sir.
What it mean? What is definition of gene disease relation? Means in a sentence, a gene and disease mention their relation, or in a paragraph, like how it is done in the
Absolutely.
table
So
in the bar.
I was just completing the architecture and just coming to this performance part that I had kept over here.
Okay.
So BioBERT
Okay.
essentially outperforms pre-BERT that we have. It takes in around it contains around 97% of BERT's initial parameters and weights at only around 60% of BERT's training computational training capacity. BioBERT is also can be also trained on DistilBERT, another iteration of BERT that can be run on local systems as well. Over here, to answer Gyansar's question, this table actually shows relationship extraction test results for the gene disease and the protein chemical. PRF, they represent precision, recall, and F1 scores respectively. Precision is again like if you remember the confusion matrix from our machine learning classes. So precision matrix, it's essentially the false true, the true positive divided by the true positive plus false
Dave,
positive scores.
uh, the question I'm asking is that gene disease relation, when there is an input text is given,
Yes.
how it is defining that there's a gene disease relation exist or not? Is it a kind of just a binary information, gene disease relation, yes or no? Or is the relation which is like a quantitative information? For example, there is a paragraph. That paragraph has multiple genes appearing. there are multiple disease appearing, how the gene disease relation numbers will be calculated from that.
The second way, essentially, like for example, if there's this paragraph where there are multiple genes and they are then located with a particular disease, then that has been used for training and fine tuning of BioBERT. Now when BioBERT is given to analyze the relationships between any set of n genes and any set of n diseases, it is able to map those genes to those particular diseases as it learned from its during its training period. And these are the specific
Um,
scores for like precision recall and F1 for all of the information that it has been trained upon. For example, when
but
BERT,
you can calculate when you can calculate precision or recall when you know already the information what are true positive, false
yes,
positive, or
it
true
was a
negative, false
validation
negative.
data set. It was not a
How do
testing
you,
data set.
yes, but how the validation data set is created? How do you know whether this gene or disease related or not? What kind of data was used here?
I mean, still like that's okay. I guess I'm able to get your question. During any LLM model or during even any machine learning model, there are like two or three different types of data sets we have. One is the training data that we use to train our models over like entire corpus, the big 18 billion corpus that we have. The second one is our validation data that we use to test our accuracy of our models. And all three of these
May
are
I
made by
interrupt?
researchers.
Go ahead. Yeah, Ajay.
So I think we're not talking about general training, like the general techniques or strategy we're using in the machine learning or deep learning model, but we are specifically talking about what is like the training site in this given data, in this given result. So like the training site, the cross-validation site, or like the test site. Okay, yeah.
Mm-hmm. I mean, I I'm pretty sorry, but I couldn't get your question actually. Like, was it a question or like you were adding information?
Yeah, so I'm asking that what is the specific data resources? I mean, like how you divide these sites, like the training sites, the test sites, or the cross-validation sites from their paper or something. So could you give us like a little introduction about this, how they did in in their paper?
The standard 80-10-10 procedure. This I'm saying
So,
this 80%
so
of the
the
data would be
question
like,
is,
I
yeah.
mean, throughout
So,
their
what
paper.
was the data?
Huh? I get.
So, I think the question is that what data was used and what training and test they did, and like, do you have some information about that?
Absolutely, sir. So they use the standard 80-10-10 procedure. I'll open this one as well for you.
80-10. Okay.
I'll open.
Yeah.
I'm getting it, sir. I'm opening it.
So, because 80-10 is also five-fold cross validation, right? They can use. So they did that.
I'm showing you the exact ye as well of how every single data is there.
Right.
But to my knowledge, as long as much as I reviewed their code, they've opened. They have used the standard cross validation parameters of 80-10-10. Like 80% of that entire corpus would be used for training, followed by
Training.
10% of validation, and then again
Yeah.
unknown 10%
So
for
this like
testing.
it will be a five-fold cross validation. They use 80-10 and then they do it five different times.
Yep.
80-10.
I'm
Am I
actually
right?
locating this. If you can see over this.
You need to silent share that window. You are sharing this
Yeah, yeah,
PowerPoint
yes, sir.
window.
Just I'm trying to zoom in over here before I share that.
So, Dave,
Is my screen visible?
can you? Yes.
This is the pre-training that has been done for particular corpus. And I'll over this, like I wasn't aware that I would be asked this question, else I would have added these results as well. I'm adding again the data that they had used.
So, these are the BioBERT which are trained on different corpus.
Yes, sir.
So Wiki, books, PMC, and PubMed. Okay, all of them. Okay, the table you are showing, that ROC performance table. Okay, if you go to that performance table, the previous slide you were showing
Mm-hmm. So I will
in the
I
slide.
will just add one more picture over here to as well.
Okay.
If you can see this, the statistics of all the relations that have been extracted. And following this, I'll
Yeah.
add just one last.
Yes. So yeah. Yeah. So this is a biomedical relation extraction database, entity type and number of relations. So GAD is what the full form of GAD? Gene and Disease Association, maybe Gene and Disease.
Gene and diseases. That's all.
So there are just 5,300. Where this relations coming from? Gene disease relation 5,300, and there are EU ADR. There are 355 only. Protein and chemical are different, but where this gene disease coming from and how they looks like, how they have been computed, they are like a real gene disease association, or is it they are like inferred gene disease association?
These are all real gene disease associations because since they have used these datasets as like they haven't computed these datasets in their paper. They have used these in order to validate their models in order to pre-train and then work accordingly in their model. So like let's say
Yes.
if I'm
So that's what I'm saying. So if they use these 5,330 gene disease pairs
yes
to
sir,
validate their model, right? That's what you're saying. They
absolutely.
use these pair of gene and disease 5,330 to validate their model. My question is how much these 5,330 themselves are a real validation? Are they known gene disease association? How they looks like, how they have been inferred that this gene is associated with that disease, where that was found. Do you understand what I'm saying?
In another paper actually, like if I can actually source that paper that I could actually share that if you would like me to.
Yeah. So
Could I
there's
share that? It was
actually in your
actually a
previous
paper from
slide,
2018, Liam and Kong. They had formed this
there,
entire
no,
data
there was
sets.
Bhushan and Nagarajan paper was there in the previous slide. If you
Yes,
go,
sir.
the slide you was just showing me with those precision recall numbers. Yeah. Just don't zoom out. Little zoom out. Little zoom out. Little zoom out. Not zoom in. Yes. Yes. So here it says the notes scores. So precision recall scores on each dataset are recorded. The best scores are in bold. The scores on GAD and UADR were obtained from Bhushan and Natarajan 2018. So the scores on GAD. What is this about? This GAD GAD?
GAN and
I
G's
mean,
and diseases data sets. That's just the data set name.
yes. Where is the dataset? I want. Is this dataset accessible?
Yes, yes. I'm actually locating that itself. It should be accessible.
There should be somewhere. It should be
Yes,
mentioned.
it's open sourced. It's open sourced. Just give me 1 minute. I'll just. How about I share it to you? Can I share it to you somewhere? Because I have this data
Sure.
on my fired computer actually. It was actually an open source
This.
paper that came in 2018, according to what I'm reading right now. And I actually never went into the dataset building. I was pretty confident about.
So this is a data set which has around 5,000 pairs. Each
Yes,
pair is a gene and a disease.
yes,
Is that
like
you're saying?
yes.
Okay.
And on the upper end, like these taskbars, if you can see these ones, these are the ones that
Hmm.
BERT was actually trained upon. When
Yes,
BioBERT was
that I
trained on this, these were the accuracy on these datasets. When BioBERT was
yes.
trained on this, these were the accuracy. And over here, if you can see, the highest has been over here. That's the recall score actually, but the highest accuracy recall has precision has been found over at 77.02 and 83.55.
Yeah.
These have been the highest precision and recall scores respectively.
So BioBERT 1.0 and 1.1
Huh?
is saying that what is difference between 1.0 and 1.1? Because it's, I mean, 1.1 is just a addition of just PubMed, or it is like a so 1.0 is PubMed PMC both. This is 1.0 state, and 1.1 say just PubMed. What does that mean?
It was the second iteration of that BioBERT particular model. I mean, like the
But
number of
only with the
steps,
PubMed?
the number of training steps of 1.0 was actually 270. Like BioBERT, BERT when it was released, it had three versions. One was the smaller version of around 17 million parameters, the BERT uncaged at around 110 million parameters, and the BERT large had around 17 billion parameters. Similarly, when BioBERT came out, it had three training steps. The smaller one was 270,000, and for the bigger one was 470,000. When version 1.1 came, it had a training steps of 1 million such steps. Like I have that entire data right in front of me. Like even when we are the next slide that I'll be showing you, I'll show a small comparison between version 1.0 and 1.1. The only difference between them is the training steps over a particular data. 1.1 had a more accuracy of around like 4 to 7% compared to 1.0. 1.0 had around 32, while that had around 38 point something percentage. I'll show it right away.
Okay.
So one,
So,
huh, version 1.0, this is
okay. Go ahead. Let's continue. Maybe things will clear later. Yeah.
sure. Like I'll just mention this one more thing. In version
Hmm.
1.0, right over here that we are seeing, like this one, PubMed had around 200,000 steps, and PMC had around 270,000 steps. When I'm talking steps, I'm talking about the training steps in order to build the model during the pre-training of the model. And this was the final version 1.0 at around 470,000 steps. When 1.1 came, it added more amount of PubMed, like the amount that wasn't like completely the amount that wasn't completely free had some amount of like private information from, like, not private, paid information from PubMed. It added those datasets as well and brought to 1 million steps, training steps, almost like more than double of what the final version of 1.0 had with itself. That was all about it. And other than this, like, there wasn't any such specific update. But yeah, there was a massive results update that was noticed between version 1.0 and 1.1 that
Okay.
comes to
Okay.
over
Let's
here.
let's carry on. Yeah. Let's continue. Yeah.
This is essentially like the previous one was actually biomedical relationship extraction between both gene diseases and protein chemicals from the ChemRoot dataset from YCONG 2017 or 18 something, and one was Balabram and Natarajan dataset from 2018. Those had the gene and disease dataset, and this one is the question answering dataset results. That is, I give the model, I give BioBERT a particular query, and it answers me specifically to the answer to my query. For example, like SLM, these are again strict, lenient, and mean reciprocal rank. Over here again, these are the results. And I guess I've made pretty clear, or I have delved quite deeper into why I have been preferring BioBERT over other pre-trained LLMs, because it has the access to these fine-tuned datasets from Bhasubram and Natarajan, from ChemRoot, and from the other question answering datasets as well, and its performance on all of these tasks, NER, RE, QA, it's better than even BERT, GPT-3, and even others. And also we can always fine tune this, which comes to the second half of my project completely. The graphs that we see over here is the one that you, this is like right now one which you are talking is the difference between 1.0 and 1.1, and what happens if we increase the data set, the number of pre-training steps, the pre-training size, corpus size, and after fine tuning, what, how does this graph look like and how does it go like. This essentially shows the
What
variance.
is this BC2GF stand for?
BC2, a data set again, sir.
What is that data set? So NCBI disease data set is maybe all the diseases.
uh, yep,
What is this database is about?
it's a biomedical
BC4
named
can be.
dataset created again in 2008, and this was solely created to evaluate the performance of BioBERT, and it stands for evaluating like every resource that I am reading. It contains a set of sentences and their corresponding gene annotations. BC2GM.
Corresponding gene annotation sentences.
It contains a
What
set
does
of
that mean?
like that's what I'm reading. So
Okay. And NCBI disease is just a diseases. So these are all just the text. These are just text, right?
when you mean text, I mean text, special characters, numbers, everything.
Yeah, yeah, yeah. But this is just text. This is not like an Excel sheet of certain other information, the other data.
Excel sheet, like how do we generate Excel sheets? Excel
No,
sheets
no, no,
also
no,
come
no.
from
The
text itself.
data, no, the data is a okay. The it depends on the what those number represents, like what kind, what the data represents, right? So this is just a, I would say this is just like a literature text. That's a one kind of data. Um, there is another kind of data, is just a list of PubMed IDs. There's one, two, three, four, five, six. That's the data, right? That's a number. That's a kind of list of numbers. So there is a, if I say there is a data, there is a database where you have just the all the genes under their names, their chromosome positions. So that's also a database. Or
Absolutely.
there is a database which are just a list of all the proteins and which interact with other proteins. That is also a database, right? So database or these data, they the question is what they represent, what they mean. So when you say these are, so they're basically these are kind of text sentences, right? They're just sentences by sentences they're put, or it is something different. It's a kind of a table of all the genes. Let's say NCBI disease. Okay, there is a, if it is a disease database, I expect it will be kind of like each row is a disease name and then the information about disease, or maybe some sort of disease identifier. So that is a more like a dictionary of disease. I do not know, but I'm just curious to know like what this database represents there. Just like remember, like when you were showing me the Google Colab running those knowledge, creating knowledge graph, the input were links, hyperlink for the Wikipedia pages. What those Wikipedia contents? Text. Those are
Text.
text, sentences, information, right? It is not a kind of a table of all the students record, not like that. This is what I mean. Because depending on what you're giving, then it makes sense. It's easy to understand like what kind of training you're feeding in to these models.
So do I open any
No,
of these datasets in front of you, right in
no,
front
no,
of you?
no, no worry, no worries. Yeah, that's fine. Yeah, we
No,
can
because
always
I
follow up later.
have
But
like I just built it over here. If we can go back to here, if you want
we,
to
we
check
can we can
this.
follow up. Okay. Yeah. So this is, I think this is performance, if I'm not wrong.
Yes, sir.
Is it a
This is the accuracy of the models on the training datasets and how each dataset performs. Providing along with this, I also wanted to add this file.
so Yubo, how's that? Are you familiar with these databases in your experience?
Yeah, I can see clearly. I mean, I'm having some. some connection
Yeah.
issues. I can see the screen clearly. I'm asking how to take a screenshot for me actually. Uh,
Uh, can you zoom?
I'm not.
Dave, little bit zoom out. Yes, yes. Then we can see the full table. Yeah. Um,
Yeah, okay. Yeah, it's loading for me. Okay. Actually, I went through this and
you know about these
these does
databases,
not
right?
look very familiar for me.
Okay. NBCI disease. I thought it's a NCBI disease. It's a typo, or is it me who's right? Can you go a little up? There was a because NCBI disease mentioned other places as well. So because I think NBCI, it is again into NBCI. Can you go in the graph?
In the graph, okay.
Graph. There was a graph you're showing. Yeah. Let's see.
It's a
So
type.
this is NCBI. Yeah. So it's a NCBI disease, and they call it NBCI disease later on the table.
Though I'm
Okay.
thinking it's a typo, I'm not quite.
It's a typo. Yeah. NCBI is a. I mean, to my knowledge, NCBI is a proper name, but NBCI.
So you just muted yourself.
Yeah. So NCBI is a National Center for Biomedical Information, but NBCI they might have their own name. Give me 1 second, Dave. So
Hello?
okay, but this is something. Yeah, this is not something important right now. Yeah, we can follow up on that thing.
Like,
Let's see.
if you
Yeah.
can allow me, I would share you this tab. Like, if you can see this, this actually
Yes, I see that.
this actually contains much more such. This is actually the source where all of these data are located. So why this data came into being, and what is the origin of this data, and how can we assure ourselves that this is the correct data. This is where it comes from. NER performance, the biomedical benchmarks leaderboard, and finally their metrics, model name, model name, model name, and how we compare everything.
Oh,
So would it be better if I could
okay.
share this link in the chat itself, and maybe everyone could just play around with these models and
Yeah,
compare the
we
metrics?
can follow up on this one. This looks like it's a kind of a table or something. Results in paper with the code. Where you are getting? Okay, the results are in the table here on the right side.
Yes, sir. No, it's kind of an it's not a table. These are all changeable parameters for every model and every data set and every task. I can change these parameters and change the
Okay.
metric to find the
Is it
final
the,
accuracy.
so is it a kind of tool which is available to play with?
Yes, yes,
Okay, it's online available, right?
absolutely.
Can okay, okay, then we can follow up on this.
Do I send the link or attach it to the presentation or anything?
No need for now. Yeah, let's continue your presentation, and we can follow up on this thing. Yeah, these will be some like follow up for later. We can do that.
Okay, give me 1 second. I'll share off my audience window. Perfect. So now that I have been able to make, I guess I have been able to convince everyone why I'll be going off with BioBERT and not, why I'll be going off with BERT and not Llama, and under BERT, why BioBERT, and how I'll be cloning that off from their online repository and making specific changes on it. Now comes an important part. Since BioBERT, that the one that we are using, has around 18 billion, has been trained on more than 18 billion tokens and has a set of its own parameters. How do we clone that to our local systems and then fine tune it according to our specific needs? For example, if I just want gene to gene interaction or gene and protein interaction and their specific benchmark results on these data sets, how do I clone it and then like execute it in code? There comes a separate section called LoRa. LoRa stands for low rank adaptation, and is essentially a method. It's not a tool, it's not an algorithm, it's just a methodology wherein we attach a set of a blank set of parameters and a softmax function at the end of our cloned model. And when we have a small subset of very specific papers that we want our model to train on and give specific information out of those papers only, then we retrain our entire model and this empty layer LoRa on this specific data set, provided like post this training procedure, the parameters and weights of LoRa get updated, and at a much lesser computational and time cost, we are able to achieve a near same accuracy on all of these datasets as mentioned on the left hand of my screen. Like, it reduces additional parameters needed for fine tuning up to by 90%. And parameter efficient transfer learning, it is kind of a like a more house way or a more standard method of transfer learning, which maintains around 95 to 98% of fine tuning with just a fraction of parameters, like as discovered from this paper. Then also it outperforms your standard tasks by 10 to 15%, as mentioned again from this paper. I'll just zoom off into this graph once again. This is the Vigo dataset, again a dataset that contains, yeah, this contains again all of the genes, proteins and diseases, the biomedical data, all of it combined. And accuracy here means of next sentence prediction, next word prediction. Prediction accuracy, this is the higher one, and this was this one question asked to me. 0 to 1 is the normalized accuracy, 1 stands for 100%, that's the full final accuracy. And if you can see the lesser one, it's actually LoRa that almost achieved 90% accuracy than the actual models, which have been trained on immensely huge servers. So we can actually use LoRa in order to bring this to our local laptops, achieve a higher accuracy, and quickly adapt BioBERT and bring it to our tasks that we intend to develop. Like, did I make sense or something? Hello?
Yes, yes.
Perfect. So it improves model performance, efficient resource usage, and makes it perfect for medical AI applications. Now we head to the limitations. Addressing hallucinations, the biggest limitations of LLM is actually hallucinations. And why it happens? Because since LLMs have this intrinsic quality of predicting other data, of predicting like information, there are certain cases when they predict information that's absolutely wrong or absolutely untrue. And to save us from not believing those information, we have these two methods. One is by using either RAG pipelines, Retrieval-Augmented Generation, or RAG, Retrieval-Augmented Language Model. Or the second half is through using knowledge graphs and graph neural networks. I'll go off one by one into which one is better, how much it's better, and why it's better. The three questions: which, how, and why. The preventive measures, and I'll just in very short over here, it explains what RAG is. RAG is essentially cloning a model, giving it a certain set of data and asking it, you need to answer me questions only based on this data. This data becomes your Bible, and you need to answer and comprehend all of my questions only from this and your previous knowledge. You need to fine tune everything on this data only. This makes it adaptive for situations where facts could evolve over time, and it's one of the best ways for generating reliable inputs. For RAG again, there is this entire methodology called LangChain, wherein you have a set of prompts that are human-like, and you feed them all directly to the model, and then the model generates prompts based on the human indexed prompts that have been fed to it. So technically the entire system works in this way. I have a set of human-like questions that I would feed into the model exactly at the beginning, and once it's fed, then the model would give in an output, and every time it gives an output, a prompt, then again the next index prompt of the user is again fed into the model, which continues its fine tuning until a complete system is established that employs RAG pipelines in order to provide more reliable outputs.
Mm.
May I have questions on this one? Post this, we will be going to our entire proposed model, what I propose, like what I've been talking about this entire time. Just post this slide, we will be going to that. Answer, like any questions? Post it.
No, all set. Yeah, go ahead.
Perfect. This one was addressing hallucinations using RAG pipelines. Now we come to this entire synergy between LLMs and knowledge graphs. Why knowledge graphs are important, and how we can build these using LLMs, how we can use these knowledge graphs to retrieve information that we want, and how proceedingly we would work. This entire flowchart shows all the possibilities, all the permutation and combinations that can occur between LLMs and knowledge graphs, right from KG enhanced LLM pre-training, LLM inference, interpretability, training objective, instruction tuning, and probing and analysis. Like if you can see over here, there are three segments, like three initial parent classifications as I call it. One, when KGs, the knowledge graphs, enhance the power of LLMs. Second, when LLMs augment KGs, when LLMs are used to build these knowledge graphs, when LLMs retrieve information from these knowledge graphs, and thirdly, when both of these work in synergy, when both of these work together, synergized knowledge representations and synergized reasoning, that the fusions. So this becomes the entire flowchart.
So, Dev,
Yes, sir.
these different options, these are like different methods where there are already some work done, or it is just like ideas.
uh, I I can't guarantee like that in all of these permutation and combination there has been work done, but these are all the possibilities. But in most of them, work has been done, and we can enhance the work that has been done using our proposition model. But
Okay.
definitely yes, the next slide that I'll be proposing, the proposed model that we have developed over time, that hasn't been worked upon by anyone. Like I tried my level best in order to search papers from Archive, Google Scholar, PubMed, and even from Papers with Code,
Okay.
but couldn't find out any model or any architecture that plans or maps out to the one
So,
that we will be proposing next.
so here it says one of them is the KG enhanced LLMs.
Yeah.
In that, the middle one is KG enhanced LLM inferences. In that one is the retrieval augmented knowledge fusion. Is it a RAG, regular RAG, or is it kind of a different thing?
Different thing. And I guess the next question would be how and why it is different. In frags, we feed in input documents. In retrieval, in the one that you see over here, we feed in the prompts in the format of knowledge graphs. In just the next slide, I'll be showing of them as well. Like I have this entire corpus of papers that talk about LLMs and knowledge graphs, and over time I have come
Okay.
to this
Yeah,
understanding.
go ahead.
So like was
Yeah.
able to make that difference very specific, because in RAG you feed in prompts that are saved in the form of documents, and in this format RAKG you feed in prompts that are fed in the format of knowledge graphs.
Yes, I
Perfect.
like that. Yeah.
Then we move to this model. This, if you can see, this everyone can see, this is just a pictorial representation of my whiteboard, and this actually is the model that we have been talking on. We have been like brainstormed into thinking with a lot of input from Gyansa. This finally comes into what we have up till now, what all of the literature that we have read up till now is essentially we parse in a query into an LLM, which then builds the knowledge graphs. What we saw right over here. Sorry. Sorry. Which we saw right over here. That how we build knowledge graphs using LLMs, how knowledge graphs help LLMs to retrieve information, and how both of them work together. Whatever corpus that has been in circulation up till now essentially believes in sending in queries, giving it to the LLMs, and building knowledge graphs effectively. What we propose is a two-stage architecture. The query would be passed on into a BioBERT plus LoRa model. Everything, whatever like I have been talking up to now, the steps that I have built, I am trying to like compose all of those into a composite structure, a composite architecture that we will be working on next. BioBERT that we will be cloning off from the internet, LoRa that we will be using to fine tune all of our smaller subset of papers, and using all of those to build, to just generate a specific result and the citations of this query. For example, if the query is what are the like I was asked this query last time by Gyansil himself, what are the PDP symptoms of Parkinson's disease, and how do you get those gene regressive those linkages? I will ask this question. What this model would do is it would give you the specific result if it's available online or if it has learned, along with the citations where it feeds those information. It can be any scientific journal, it can be anything from PubMed, PMC, or it can also be from anything like any other scholarly article available online. It gives these citations, which is then fed to the second half. The second half is another LLM sitting right there, DistilBERT or Llama, which I'll again come to why I'll be using these, and this model will then build these knowledge graphs. So we again come back to here, this one, LLM augmented KGs, LLM augmented KG generation, and this entire plethora of like options or permutation and combinations. This will be the second half. Again, sorry, again if we come over here, so this one was one example that I had found on as how LLMs work in synergy with knowledge graphs, how LLMs can be used as agents for reasoning with GAs. Which country is Barack Obama from? It is passed on to here, and this is the graph available. This is the graph fed into the system already, and an LLM goes into here as the agent. The red lines that you see over here, the red lines that you see over here are the connections built by the LLM when it reads the query input. It goes all the way from Barack Obama to born in Honolulu, city of USA. This is the final result or the final node that comes off as output by the LLM from the graph. I want to like very much emphasize on the words I am using, by the LLM from the graph for any particular query. It's kind of like democracy, by the people for the
One third, Dev,
people. Sure, sir.
um, can you go to the show that figure again, the
Sure.
Barack Obama? So you're saying that reasoning on graph. So when that person asks question, he asks the question to the model, LLMs and KGs combined. Like that's a set.
Yes.
Can you explain this figure again? There's the LLM agent,
Okay.
and then there's a knowledge graph.
Hmm. And the question comes off, each token of that particular question or that query is passed on into the LLM. We read that entire architecture right now about how every single token is passed off into the encoder, then again goes to the decoder and comes out as an attention matrix. The important entities of this question is country and Barack Obama. It searches in the entire graph the position of Barack Obama and needs to find out the like the country that it belongs to. So it goes off to the next
So
adjacent
does
node.
it mean, yeah. So that means that we need to have already pre-built knowledge graph to answer this question, right?
To answer this question,
Yeah.
yes. This is,
Okay.
I mean, this
Let's
is the
say,
model itself. LLM plus KG.
yeah. But the thing is that when you ask the question, that the knowledge graph has to be there. The actual data in the form of the graph is should be there in the database.
That's essentially what we are building over here. Throughout the
Okay.
architecture that I just explained, that we are will
Yeah.
be using BioBERT, LoRa, then giving it to DistilBERT, Llama. We are
Yeah.
building this KGs right over
Yeah.
here, and then this KG will be used in this way.
Okay. 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 Now in this case, what is this LLM? The yellow color you say LLM agent.
Mm-hmm.
What is this one? Which LLM you're talking about? Because you always take the name, right? One
Absolutely.
particular LLM.
I'm really happy you asked this question. Over here, my personal idea was to use either BioBERT or DistilBERT. In this case, because of a set of reasons again that I'll be proving again in the next couple of slides, why I'm using these slides. But again, I'm open to experimentation as to which LLM performs better, because
Okay.
DistilBERT is just a smaller scale BERT. BERT, the bigger, the massive dinosaur. BERT is like the dinosaur in the room. and DistilBERT is just like a reptile with all the scaring abilities of the dinosaur. Like I don't know if I'm able to draw
DistilBERT.
that
Okay.
analogy.
Okay.
So this is why I'll be using like DistilBERT or BioBERT for this case. But again, I'm still open to like understanding
Yeah.
from this
Yeah.
entire
So
pipeline as to which LLM would perform better according to previous research data, according to previous
yeah.
literature, which has a better possibility of working. If you can just
So
focus on,
yeah.
yes, sir.
Is, this is something is a kind of some publication. This LLM, these figures, this and the previous figure.
Mm-hmm.
Is it some sort of literature you are reading, or did you just made it? I don't think that you made it, right? It's some literature from online, right? Where you can read something
The
about it.
second one,
Basically, LLM
the
and graph.
second one, Barack Obama was like one I had made, and the first one, this one was
Uh,
literature. This is literature.
Even the previous slide, this one, yeah.
It's literature.
So I'm yes. So yeah, I would like to. This is more like a brainstorming ideas because here it provides many different ways how the LLMs and knowledge graph could be put together. Yeah, because the things which we like discuss is just one of the way, right? There could be many different ways
You
which
could
could be
choose
more
any of the
effective and
permutations.
they might have pros and cons. Yeah, so this will be something worth have more brainstorming in future. Yeah, but
Absolutely.
let's continue.
It's kind of
Carry
like
on. What
even
do
if
you
you
say?
can just count all of the possibilities in here, you can actually merge any of the ways of using KG enhance and with any of the one with LLM augmented, then finally synergize it. There could be an
Yeah,
n number of ways by which this entire architecture could work, and we could never finally reach to the one that's best for us. But it's kind of like continuous R&D. So every single time we just need to keep in mind
yeah,
that we are improving our accuracy results, we are improving our F1 scores so that we get to a better
yeah,
stage. If you can just
yeah,
open on this smaller part, stage 1, stage 2 and stage 3. Stage 1 is building those
yeah,
knowledge graphs and using those knowledge graphs to retrieve the specific information that we need. Stage 2 is
mm,
combining them into a single multimodal agent that has an LLM as an agent and an information as a knowledge graph. And stage 3 is now uploading all of these into Neo4j. That again comes to a separate topic in itself. How I would combine
yeah,
Neo4j and multimodality in order to like portray that information to the scientist or the user who is using it. These are the three different
yes, yeah,
milestones of unifying these
yes,
two blocks.
yeah, yeah. Sure, sure.
If you go to the stage 1 of our proposed model, stage 1 was essentially we given a query to BioBERT. We pre-train BioBERT with our LoRa. We feed in a specific
Where
subset.
is your mouse? I cannot see what you are hovering. Can you hold your mouse? Yeah.
BioBERT,
So stage one is BioBERT plus LoRa for
yep,
query processing. Okay.
LoRa enhances this by fine-tuning it for very specific tasks. What it does, it inputs a biomedical query to the model, and this model then finally gives you the entire set of citations, the entire set of results as output. And this is a system architecture as defined as this paper itself. And this is
Okay.
the entire flowchart that shows how things work. Over here, we
Okay.
find the query processing system. We
This
took
flowchart where it starts. This flowchart is
the
little
data set right
confusing.
over
Where we
here.
start?
The data set,
Data
as
set.
Jose just mentioned to me about how we would be differentiating into training set and testing set. It goes off from
And
here.
this data set is about what? This is the data set of what?
Biomedical textual literature.
Oh, it's just like it's just a PubMed like corpus, you mean?
Yes,
Okay.
but
And then you
you
put
can
the
always
split
use
it
a
out
different
in.
data set instead of this. You can always like considering you have an
Yeah,
Excel,
okay.
you have an Excel data, or you have a different kind of like database of considering gene to gene interaction or protein to gene interaction. You can always like substitute this data set with your specific one, and I would still assure you that this entire architecture works for that as well. So this is then distributed
Okay.
into two sets: training and testing. Training goes into here, fine tuning and keyword extraction, seed keywords.
Hold on. The training goes to two different places. Fine tune and keyword extraction, and then from the keyword. This this and what is the goal of this here? This workflow? Test results.
Fine tuning
I'm trying
BioBERT
to.
over a specific subset of our literature to produce a higher accuracy and specific results that we need.
Okay. Okay. So correct me if I'm my understanding, but then why it is saying training and okay. So pre-trained by BERT and it. So I see the pre-trained by BERT. So training set the data fed into combined with the pre-trained by BERT. Am I right? That's
Yes.
and then is you call them extension. I think that we are using the word BioBERT V2 or BioBERT plus LoRa.
Exactly.
Is that I'm
Yep,
okay?
exactly.
And then pre-trained. What is KW BioBERT then? Keyboard BioBERT. Okay. Then and then fine tune goes to tune by bird. Can you explain slowly? Okay, I'm taking this thing from a simple way. Okay, let's say our data set is corpus. Let's say from the corpus, I give you 100 different papers. Okay, that means the corpus of like the whole text of 100 different papers. That is going to training set. Then what happened from this 100 corpus?
80 comes here, 20 goes here. Now
Yeah,
this
so let's
80,
say training. Yeah, so 80 comes here. 80 there are 80 papers are here. Then what happened to the 80 papers?
it is
Yeah.
distributed into three segments, like almost around 40, 30, and 10. This
So
30 and
40 papers will go in the okay. So those all those 80 papers go to three different, or it is like a 40 papers in keyword, 10 papers in fine tune, and rest of the paper in other fine tune. Is that you are saying, or
actually
is
if
it
you can
all the
see,
going?
if you can just notice over here, all of these are essentially till the end again being fine tuned. After we have
Yes.
pre-trained like keyword BioBERT, every of these papers is again being fine-tuned. So essentially, it doesn't matter to which pipeline any of those 80 papers go. Everyone will be fine-tuned till the end, and then again fed. Like fine-tuning
Yes.
essentially means like
But the thing is that it goes differently, right? These goes to fine tune there, but they go like for example, let's say I have 80 papers in training set. 10 paper goes directly to fine tune. 20 paper goes to this BioBERT fine tune, and then rest of the let's say 50 paper that goes to a keyword extraction fine tune. Now
sure,
the result outcome with this will be different than if I have like a 40 papers goes to fine tune directly, and then just 20 papers in BioBERT and 20 paper in keyword, right?
no, sir.
The results might be different.
I'm
No.
pretty sure that the result is never affected like that way, because what we are trying to understand is like how we are like like choosing randomly papers and going into separate segments. This could also be an architecture where like all of the 80 papers go through all of the three pipelines. It's just
Okay,
they
yeah,
go
this
through
is
it
what.
parallelly.
So all the 80 papers, yeah, this is what. So can you explain me what these three different routes are to fine tune? What they mean? Why they are three different? Why not just one? What they're like? What make them different?
Perfect, sir. We have our pre-trained BioBERT over here that's essentially just cloned from the internet.
Hmm.
All of the 80 papers they come over here. Our pre-trained BioBERT gets fine-tuned over here to form tuned BioBERT.
Okay.
Okay, all of the 80 papers then again come here, and BioBERT is used for extracting the keywords from those 80 papers, the tuned BioBERT. Okay.
Okay. And when you say the keyword extraction,
Huh.
so that from the tune BioBERT, it will do the keyword extraction.
Yes.
I'm slightly confused. Uh, okay. Just um. Okay. Yeah. Okay. You keep explaining me. Then I'll ask question. Yeah. Let's see if it's clear to me. Go ahead.
Once keywords have been extracted, these are again like expanded into the final keyword set. Like we already have a set of seed keywords, then this is merged with the keywords that are being extracted by the tuned BioBERT over this entire set of training papers. And once this final keyword set is performed, it again comes over here. Now again over here, pre-trained BioBERT, there is this small extension added. This extension is of LoRa over here. Tokenize process the input query using the fine-tuned BioBERT plus LoRa model. It's added and again brought over here. And this entire set of 80 papers is again brought over here. All these extended set of keywords, the extension of BioBERT with LoRa, and the entire set of training papers is then utilized for fine tuning, and we finally have a tuned keyword BioBERT, which is then used for testing with the starting में जो like the 20 papers that we had kept aloof from everything, and finally we get the test results. Like, was I able to
Is this
clear it?
model okay? Is this the proposed model somewhere working or no?
This is the
Can we
that
see a kind of an instance like how this
if
works?
if
Like,
you're
is
talking
there
about the
somewhere?
code, yes, you can see, but if you're talking about the output, I'm sorry, sir, that hasn't been
No,
completely
no.
envisioned.
If the code is there, yeah, if the code is there, can we just like say kind of a hello world program?
Sure, sure,
I can I see how it works? This whole thing is working. Is there any way you can show it?
absolutely, sir. I just need to share my tab.
Okay. This workflow is a part of any literature or it is you made this workflow?
Kind of both, sir. Like, it is there in
No,
some
no,
literature, and I prepared some of it myself.
no, no,
So
no. This workflow, is it
only
a
the
kind of
workflow,
you?
yes, it's there in literature, but the extension, this if I were to talk about this extension, it's not there.
Where is your mouse? Okay, okay. Yeah. Okay,
This
I
is
get to
not
see
there in
that.
any workflow, any literature. This is there in, like, I
Okay,
prepared this part, but the existing, this entire workflow, you can find it in literature. I'll attach all of those papers as well. These are only the links.
okay, okay. So you are showing something, right? You're going to show something. Yeah.
Is it there?
Okay. Yes. So let's say so this is the uh, so yeah, yeah. Can you explain a little bit
Sure.
about that?
Loading in the untrained BioBERT version 1.1, 1 million tokens, loading it from pre-trained. Now defining the LoRa layer for self-attention mechanism. What it does, adds the extra layer of null features. That sends an extra empty layer that will be fine-tuned according to the specific
Give me
subset
one
of
second.
corpus
No
that we will
problem.
be giving it. Now this function, apply LoRa to self-attention. This is like if it is an instance, and it just adds the LoRa layer to our pre-existing BioBERT that we have over here, 1.1. It adds the LoRa layer over here. It adds the LoRa layer over here, and to get self-attention right here. The dataset loads this squad v2 dataset, and I've just used an example biomedical dataset, and this again pre-processes all of that as well. I have this entirely. Once this is pre-processed, if you can see over here, this is BioBERT tokenizer that we saw over here. This part, is the architecture and the code making sense? Like, just even the slightest? The BioBERT tokenizer is being used for extracting the keywords. If you can see over here, for this loaded dataset, the tokenizer takes in the examples only second and returns the keywords of this new, the training set of the data. It goes all the way up to here, and this is the fine tuning, like BioBERT plus LoRa, updating the parameters of the last softmax layer function in order to have that entire composite, this architecture, this place, like to reach here. To reach
Mm.
here, this is the part of trainer, and this is the part of tuner of BioBERT. How about
Oh,
I show it to you, like both in one screen? I guess that would be better.
I can yeah I can adjust that. That's fine.
Is it fine, sir? Then I won't do
Um,
that. Otherwise, if you
yeah, yeah, yeah. No worry. I know it will be tricky for you, so
no, no,
yeah,
it's
no worry
just
about
a
that.
30-second task. I can do it.
So in the code, yeah, in the code,
Yep, ready?
Yeah,
This one was one I was talking of, when BioBERT
yeah.
tokenizer tokenizes all of this information from this data. This is here.
So yeah, can you? Okay, I think that this is something I would like to dig further. Maybe not today. That when you because you're right now loading some data. So how this data looks like? What is this thing? Is it
That's
a
an example data set, sorry.
efficient?
Like I want to make sure that's just an example biomedical question
Yes,
answering data set. We need to
yes, yes,
feed in
yes.
our specific data set that we want, and that would essentially come from a
Yeah,
subset of PubMed PMC anywhere.
yes, yeah. So yeah, so do you think that this code could be usable if we have a different set of data which we want to put
Absolutely,
to
sir. I'm
train it?
still debugging this,
Okay.
actually this entire procedure. This is actually throwing me a small error over here, like in the
Okay.
standard training arguments error. So that's something that, like, I can
Yeah.
debug and make it. I can fix it.
Yes,
So
yes, yes.
once that's done,
Definitely. Yeah.
like this architecture is almost ready. One wherein we
Yeah.
use training arguments, this part,
Yeah.
pre-training BioBERT, and then adding the LoRa layer. If you can see, we
Yeah.
use the BioBERT model, training dataset, validation dataset, and we have a very specific parameters as well that I'll show you to in the stage 2 of this proposed model. What are the hyperparameters that I will
Okay.
be using in order to build every single step? What would be the learning rate, the batch size, the number of epochs, the number of per
Yeah.
device training batch, and even the
Okay.
decay, the gradient descent weight. So I'll be showing everything of this.
Yeah.
Once that's done, it just generates responses, and this was one example usage, one query.
Yeah. Okay. Yes. Yeah.
Is my so I just wanted to ask this one question: is my architecture and my code making synergy? Like,
Yes.
do you
And
work
this
in?
is where I think that I would like to have more discussion on this thing.
Sure.
I mean, slowly I'm getting. Yeah. Um. So. I mean, I would like to follow more on this thing. Yeah. So why don't you continue? You're showing stage one now.
Absolutely, sir.
Let's see stage two. Right.
Okay, sir. 1 second, please.
So the stage one will be. I think that in this workflow, I get little not clear because at a stage one you create the knowledge graph, right? The first thing is that.
No, sir.
Um, no,
Stage one
it
is
is a test.
creating the specific text. Stage two is creating knowledge graphs. Let's again,
Okay, yeah.
I'll
So can
come
you?
up to
Okay,
this
okay.
one again.
So in your board, the whiteboard cartoon, you show that thing, right? Can you show your whiteboard cartoon that how it is connected to the bigger picture? Stage one, you get the text results, a proper text result.
This is stage one.
Okay, specific results. Okay. So when you ask query for a query, it goes to the model which is trained with the BioBERT plus LoRa. It gives a specific result, right?
Yes, sir.
Plus citation. That's the stage one. Okay, one question here that let's say if I'm asking my query and LoRa is a pre-trained, right? So that means those 100 papers which I give citation, let's say 80 citation, no, not citation, 80 um, no, what I'm saying that how you decide what is LoRa here for different question. What I mean that let's say my question is coming that okay, what is the role of T53 in cancer? That means my specific fine tuning articles are only those cancer papers, or maybe fine tune article could be some additional subgraph, like a subgraph of data. So I'm using the subgraph is a kind of another data which we have, let's say. Then do you think that if I provide you that, would it help? Yeah, hello.
Yes, sir.
So what I'm trying to understand the LoRa part. It
The
is
amount that I am getting is like, you want to ask like, what if the background of query changes? For example, if I have a query like, what is the role of TP53 in cancer, and my second query comes out, what is the symptoms of Parkinson's disease, or what is the gene to gene
yes.
interactions?
So yeah, so do you think that they should have a different LoRa component there?
You can increase your LoRa component. You can increase your LoRa component to all the data that you want to ask. If you feed it with, at the same time you feed it with both cancer data sets as well as Parkinson's data sets, then it becomes much more ready and efficient to answer both its answers, both its questions.
Um, the only thing is that when we and okay, and okay, this is something. Yeah, we need to dive into this part. Okay, let's yeah, let's think like let's say with this, let's say assume it's working. Yeah. Okay.
So this is stage 1,
We got to that.
and finally stage 2. Stage 2 was what we had kept over here: DistilBERT or Llama and KGs. I would request for a second, please.
Mm-hmm.
Sorry. Stage 2,
Yeah.
the square off between, are you not seeing my complete screen? Why is it coming this way?
You you had to little zoom out
Is it
because
better?
you cut the on. Yeah, but you see the little bit of on the right side boundary you cut. If you zoom out a little bit,
No, sir, nothing is being
we
cut.
can read the full.
Like, this is the full thing only.
Okay. Okay, got it. Okay, that's fine.
So like, actually I had much content to put in one slide now, so things appear as if they are bleeding when
Oh, okay,
actually
no
they are not.
problem. No problem. Yeah, go ahead. Yeah, go ahead. Yeah. Let's see.
This is this one question between DistilBERT and Llama. And what's DistilBERT? DistilBERT is just a smaller Chinese version of BERT, like not essentially developed by China. I'm sorry, but it's kind of a smaller, faster, cheaper, that can run on your local machines, almost good as your BERT itself. It retains 97% of BERT's understanding and runs at 60% faster.
Um,
That's
uh,
essentially the trade-off between BERT and any like local of this. Sorry, I just had a blackout. Sorry. And the second part comes of Llama. Llama, known for its large scale capabilities, handling complex queries, and generating knowledge graphs. Which one to use? Why to use? To create these knowledge graphs. Hello? Okay, okay. Sorry, sorry, sorry. Sorry. हाँ 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 ओके, आई एम सो सॉरी, मैं मन में निकल गया. कब बोलना नहीं चाहिए. सो सॉरी. हाँ. ओके.
Hello, Dave. Are you still there?
आई एम सो सॉरी सर, आई हैड अ नेटवर्क एरर, लाइक आई जस्ट got
Yeah.
disconnected.
Okay.
Okay.
Okay. Okay. Go ahead.
It's I'm sorry, I just need to restart a second. DistilBERT and Llama. DistilBERT contains around 97% of BERT's understanding, being 60% faster, much better to that of BERT, because we can run it on our local systems. It's more powerful and it's cheaper and faster, and we can actually afford that. But Llama, it's one that's used for large scale capabilities, for handling complex queries, and like a much greater scale. The second one that we have is the systems architecture of processing BioBERT outputs. The second step of this stage 2, if I'm able to make sense, it takes output from fine-tuned BioBERT plus LoRa model, and this is then fed into the DistilBERT or Llama. That is, we take in the output given by the previous model and feed it into this newer model. Following this, we create the knowledge graphs, the nodes, edges, and entities. That is, we always have these 3 steps in order to create the knowledge graphs. First, we have the named entity recognition in order to recognize the nodes of the particular graph. Then we have the dependency parsing or the relationship extraction between the nodes, so that we understand how any two nodes in that particular graph are related between each other. And third, we have the like displaying them or building those graphs, attaching weights to those like edges right over here. Like if we have these medical knowledge graph, if I would just zoom, like, am I visible?
Yeah, I can see that. Yeah. So even if you keep it smaller, it is readable. At least to me, it is readable. So it's fine. Yeah.
So Hausu sir and Yobo sir, are you still there?
Yeah, I'm still here.
Okay. This essentially
Okay,
shows
go
you
ahead. Yeah.
how each one is being used. KG enhanced LLMs, LLM augmented KGs, and the authentic synergy that works in between
Oh,
them.
okay. This is funny thing is that this the graph which you are showing
Yes, sir.
is coming from some literature, right? Because it is a Parkinson disease graph. I can see
Yes, sir.
it came from Parkinson,
Yep, yep.
right? Is it some paper
Yes, sir.
which actually tried to address Parkinson?
Yes, yes. Pink one is
Okay, yes.
kind
The
of a
sent
gene, I believe.
actually this is very good. So I tell you that in a tool like this in the future, this is what I want here. Do you see? Do you know what is pink one here?
It's a gene, I guess, that causes Parkinson
Yes,
disease.
yes, yes. Now it recognized pink one here, which is fine. But then it had motor neurons. Uh, I mean, okay, I'll not go into detail. But the thing is that this is what I want. A very this knowledge graph should be able to identify the right entities before putting them into the graph, right? Otherwise, the graph will be too crowded. A lot of things will be just redundant from the like a usable perspective. So let's say, for example, here in this medical knowledge graph, for me, I'm more interested to see, okay, pink one causes Parkinson's disease, also could be a disorder, but I know motor symptoms. Actually, tremor is a part of motor, like a, should be connected there. Anxiety is not required for me. Language underdevelopment not required for me. Pervasive development disorder not required for me. You see here, these are all could be the nodes in the knowledge graph, if I'm not wrong.
Yes.
But like 50% or 60% of them are useful for me, and others are like a redundant. They're not useful. I'm not saying they're noise or they're wrong. It's just that they're not relevant.
This relevancy, I guess,
Understand?
that needs to improve through multiple iterations.
Yes, and this is where we add a one more layer on top of knowledge graph. When you have visualization, I'll tell you that it is okay that we have the full knowledge graph. Let's say it's like a full dictionary. We have the full right. But what we are looking at is just the content of a piece of that in visualization, right? Because when we start analyzing the data, we want the purpose of visualization is to further get the insight from the data by superimposing some other data. So I think that yeah, let me not divert you from the main your idea here. Let's go and then we'll follow up on this one. Yeah,
Sure.
go ahead.
Generating knowledge graphs and then finally using it for visualization by giving it to Network X or Jeffy or uploading them to
So
Neo4j.
step one, I think that this is what you're saying, right? Is step one, two, and three and four,
Yes, sir.
right? These are four steps there. Okay.
The four steps in stage two.
The system architecture, process BioBERT output from the fine tune. um, the left figure. Can you explain a little bit of left figure?
The medical knowledge graph
Generate
or the
knowledge
upper one?
upper one.
If you can just
Oh,
notice over
both. I
here,
mean, just
there
explain
was
that what.
three
Yeah. So
separate
what I'm trying to
independent.
say that when you put the figure, explain me what is your purpose for the figure. What do you want to say from this figure?
Absolutely. If we can check over here again in this flow chart, there were three segments.
Mm.
One was using KGs to retrieve information, using LLMs to retrieve information from knowledge graphs, using LLMs to build knowledge graphs, and finally when both of them work in synergy. Over here,
Mm-hmm.
when we come over here, this is essentially what these three are. One is using textual input. KGs give structural fact, domain specific knowledge, symbolic reasoning to the LLMs, and the LLM act as the agent to find out, to retrieve information from the KG specific information and give that as output. The second one, KG related tasks. When we ask the LLM to build a KG, it takes general, it gives general knowledge, language processing, generalizability to build this KG and gives that as output. And when these two combine, it becomes a synergy.
Okay. And one example is that, let's say I have a full knowledge graph, data
You have a
built by a knowledge graph.
knowledge graph.
Yeah. So that means that we have this knowledge graph, which we do not know how it is prepared. Let's say another group, or we are working with another company who already built the knowledge graph, biomedical knowledge graph. That means we have the data. Okay. Now we want to utilize this knowledge graph. How would you utilize here?
This,
Do you know what I'm saying?
yeah, absolutely.
So,
This is how we would
yeah.
use it. We use
So knowledge
the,
graph is there.
like just the example that I just gave about Barack Obama and where he was born. We feed in the
Yes.
knowledge graph of Barack Obama, his entire database into the LLM, and the LLM acts as the agent. It goes off into like deciphering every single node, finding its correct path, and gives the final output by retrieving information from the knowledge graph. This is essentially KG
Okay.
enhanced LLM's architecture. Like only difference being that
Okay.
I gave the example of Barack Obama was a common sense question answer, and the one that we'll be using will be essentially med QA question answers.
Okay. Okay. So remember that I can provide you the knowledge graph data.
Okay.
Let's say the full knowledge graph data, which is even more trained on much more data. You're right now talking about just medical literature, right? The other biomedical knowledge graph data is actually even also trained on different databases along with the corpus.
So that changes the
Many
course of
things.
our project completely. That
No, but it's finally it's a knowledge graph. So,
absolutely.
but that knowledge graph is trained on a huge amount of data, which we can go into further detail. But I think that in a kind of an outcome of that, that you have a knowledge graph exact data, knowledge graph. Remember?
Absolutely.
So now how can we build on top of that knowledge graph to like a smaller size network and asking the questions? So remember that we have that thing actually.
How about I show you this next slide if it becomes a
Sure.
little better. If you can see this left section, this is essentially the entire architecture that we want to develop. This is what each section brings into the synergy. LLMs bring general knowledge, language processing, and generalizability. And knowledge graphs bring explicit knowledge, domain specific, and the specific interpretations that we want. Building all of these are from this structural facts, be it in the form of databases or Excel sheets, text corpus, be it from PubMed, PMC, and all of the online available text, images and videos, not for us. It goes into here and goes through all of this. Prompt engineering, like for a fine tuning procedure, prompt engineering, graph neural networks using Neo4j and GNNs in order to specifically retract information. Then we also can, like this is again a loud thinking of my mind, we can also deploy feedback mechanisms in order to understand that every particular answer that's generated at each step is correct factually or not, by comparing it with information online as well as with information like that was fed to the LLM in the beginning. That comes over here. Representation learning and few shot learning. Few shot learning is essentially a very like a very R&D specific topic of meta learning. Meta learning like it comes from few shot learning comes from there, which essentially means that we would train our model on very small amount of data and then ask our model to give its testing on a larger amount. That's essentially the opposite that we do in classical machine learning. We train it on a larger data and test it on a smaller. We do the opposite, and apparently according to some algorithmic tunings, few shot learning has a higher accuracy than the classical machine learning algorithms in very small and discrete topics, of course, but there are such
Mm.
literature available, and then we can apply all of these to either a BAIKJ that you had shown me the last day, biomedical
Mhm.
biomedical instructor knowledge graphs, or even a recommender system, or anything accordingly. And these are the hyperparameters for this stage 2, KG embedding and
Mm.
KG completion. So
Okay.
did I make sense over here?
Yes. Yeah. Yeah.
Yeah,
It contain
actually, I just have a quick question, if
sure,
you
sir.
don't mind. Yeah, I was just curious, how do you plan to, like, you were talking about using large language model as an agent to query your knowledge graph, right? Yeah, I was just curious, how do you plan to implement this process? Because as far as I know, there are like multiple ways to like using a large language model as an agent to like do something. I was just curious, how do you plan to use large language model to query the knowledge graph or enhance the response?
Do I share off my code for that as well?
Um, yeah, if you have
You
the
can
code.
tell. Yeah, you can show that. First, you can explain that you can show the code.
Sure. I actually
Uh,
have. I mean, the code that I would show for that person about for that percent of using the LLM as an agent. It's in a very vague format. Like I haven't completely brought it in a solidified format, but this can definitely be used, and it has been proven because the image that you are seeing on my left is actually taken from a journal. It's a literature journal that I was like when during my research, like I found it, and they have mentioned their papers as well. They've mentioned their
Yeah,
code.
we totally understand that it's a doable project or doable way or doable strategy, but we probably want to see how you implement those things, but not the general talk about those things.
Okay.
How you
how you
plan to
understand?
implement those things?
Yeah.
Okay.
So I think that yeah, this will be. Is it your last slide, Dave?
My I have another.
Yeah. So I think that Jose, what the goal was today that Dave recently actually just proposed the idea he wants to do internship. So I asked him to put a proposal, and once you see that this is interesting, then we can actually ask him to further go on implementation part. So I think that what we can do that maybe we can give some like already questions they've got from us you, and then he can follow up on that and come up next time to give a more detailed about the methods and the implementation part. What do you think, OJ?
It sounds good to
Jose?
me. I'm not sure how
Yeah.
how do you think?
uh, is house
Um,
there? Yeah,
yeah, I'm
sorry.
here. So what I'm thinking is this is like a very good interview or introduction for the large language models and like the methods in those things. But
Mm-hmm.
I mean, this might be too general. I mean, too in a
Yeah.
general level of the discussion. And
Mm-hmm.
for the citations or like the paper or the experiments mentioned in the slides, I think it's a little bit old.
Yes.
So
Yes,
to my
that is.
knowledge, there are since the GPT-4 or GPT-4 has and achieved a very high level of performance with the like the RAG strategy and
Mm-hmm.
about like embedding the query and the information together to as a as a like a prompt. Those kind of strategy has been, I think, very well used in the, I mean, in a very large domain like the industrial stuffs. So I can show
Yeah,
some
but
example
so
of that.
but do you
But
think, but they, I think they are not free, right?
actually, this is only about strategy. We could use some open source model to do the similar thing, I think.
Yeah, I'm
But
trying
it
to do
requires
something.
to have like something like a hardware requirement or the software requirement. So I mean, this is like a doable strategy of doing those things. Like we could use that strategy to build application. So I think this is applied level of the like to the final goal is to build an application to do some very specific work or specific task.
Yes,
Am I right?
yes. We want to build a specific applications which could actually we can interact more like ChatGPT, but it will be more focused on biomedical research as well as it will have a provide like a knowledge graph type
Yeah,
visualization.
so I've just Googled, like using Google Scholar to do some very basic literature research, and it seems that we could use, yeah, they are mostly using something similar to the modern or little more modern model like the Llama or the GPT to do the similar thing. For example, for the gene and disease, um, like affiliation issue problems, I
Would you
think
like to share your screen? How's you want to share your
I'm
screen?
just do very basic. I mean,
Hmm.
Google search for all those things, so it is okay to do so. But yeah, let me take a look again. Hmm. Yeah, and I think they are doing something for several different tasks. So let me take a look of those things.
So, Jose, would you like maybe next meeting you can just share with us a little bit what you're doing and what you think about could be the right way to do?
Okay, sure, definitely.
Yeah. So then we can think about like how we can actually change, how we can work together on this.
Yeah. Just because based on what I researched in the recent, I mean, in the recent 2 years, like 2023 and 2024, I mean, those papers, I found that a large amount of the using like the prompt um, to design a very specific and prompt to do the similar stuff,
Yeah,
like to
that's
find the
that's fine.
connections between the gene and the disease. So that's mm, yeah. So that's why I'm thinking that the literature review we've done in the slide might be a little outdated, I think.
Maybe. Yeah, definitely.
Yeah.
I
Uh, yeah, since we are waiting, I also want to talk about what I have some questions
sure.
about stage one. I feel like we are kind of overcomplicated the process. Because in my understanding, please correct me if I'm wrong. In stage one, we are only trying to find keywords from the query, right? Uh, we are fine tuning all those things. Yeah, and I think your current strategy was to fine tune BioBERT or some variant of BioBERT to identify the keywords. And yeah, that is a good way actually. Yeah, you will want to do it in the long run. That might be unavoidable. But for now, I think since we don't have a very strong data set of keywords, like ground truth keywords, like we don't I don't think we have data set of queries and the keywords in the queries. So I don't think we have uh, uh, it might be too time consuming to fine tune the BioBERT either. And I also think, in my understanding, LoRa is only suitable for fine tune very big models. And BioBERT, in my understanding, is not that big. We can totally just fine tune it either on Google Cloud, I mean, either on cloud on our local machine uh, very easily. And if we can fine tune the full model, I don't think we need to use LoRa since the upper bound of fine tune with LoRa is full model fine tune, right? Um, I think to identify keywords, the easiest way to nowadays the easiest way is just we ask large language model to find the keywords for us. We just write a prompt, say we ask Llama 3, please find the keywords in these queries, and I think Llama 3 will help us to find most of the queries, most of the keywords in the queries. What do you think?
So one question, Ipo, that is this Llama, we could develop an application without paying anything?
Yeah, I think Llama 3 so far is open source, and I'm not sure we can do it like for commercial, but at least for research, we can. I think we can do anything we want. We have a lot of lab mates that are like either fine tuning it or just use it for their applications.
So like if I have your
Yeah.
permission, can I
So,
show you a
so
result actually? This
what is,
entire like one that you said about we can actually extract keywords from biomedical data and how we can
Yes.
create knowledge graphs. I would just take a moment to just show you a code and its associated result that actually like even during my presentation like I had mentioned about this trade-off between BERT and Llama, BERT versus Llama, and why I finally chose BERT instead of Llama. And I would like to show you a small code excerpt and also the code output, as in why we had to resort to this entire complicated architecture of fine tuning BioBERT and not just giving it to maybe just a ChatGPT prompt to find out the nodes and weights. How about I share my entire window and there I hope I'll be able to show.
I'm going to
If
share
you can see
this
over here,
with.
this was actually a text that Gyansar had given to me, and this is actually a biomedical text. If we, I'll just zoom over here, the model that I'm using over here is BERT based on case, absolutely no fine tuning done. And if you could just ask me, I could just replace this with Llama right away as well. Like I would just require around like 5 minutes to just change it into Llama because all of the other properties remain the same. What it does is it takes in a biomedical text completely on multiple neurodegenerative diseases, including Alzheimer's disease, forms microtubule associated protein,
so
tau,
this is actually an abstract from
an
a
abstract from
publication.
a publication. Now, like I
Yeah.
just want to focus on what are the actual nodes, mutations in MAPT gene. That is, how about I share this doc as well? That would show you.
Yeah, so I'm thinking that the easiest way is trying to put the whole sentence into chat, something like ChatGPT or Llama to get the keywords
Yeah,
extracted.
exactly.
And
Like,
you could cite how many keywords you could get from the large language model.
and
Yeah.
sir, I want to show you exactly why it will not work. Like I, so this
Yeah,
is absolutely an idea. So we have the when we started our entire process, we started by giving it ChatGPT or any
I don't
one.
think this is. I mean, I don't think it cannot be worked on large large language model as ChatGPT or something. Yeah.
Sir, I'm trying to show
I
you.
think it definitely could be, yeah. So I can get the input text with the keyword extracted from the large language model. Yeah, they know the domain knowledge of those things.
This is the
Mm.
input text.
Yeah, could you
Okay.
put it in the chat? I will generate the extracted keywords. Yeah,
Okay.
This is the input
Why don't you
text
just copy paste this
yeah,
into
send
the
it
chat
into
window?
chat.
into what?
yeah.
So
I
can
can
you put this copy this text into chat window so you the Hauser can actually use this and just to run it on Llama and
Sure,
see
I
LLM that
mean,
whether
yeah,
they
I
get the
mean,
keywords.
so I have a ChatGPT open, so yeah, but not Llama
Let's,
currently. Yeah,
sure.
yeah.
Go ahead.
Let's see. Yeah.
yeah. Let's take a look.
So you take a look on that, and I'll bring you what the output of any fire pre-trained model gives in. I'll go up
Okay.
to here.
Let me make a
This
copy
is
of
the
those
text.
things.
It encodes this particular text, takes the last hidden text, take these nodes, edges. Once these are given, it creates a data frame, nodes embeddings and edges weights, which finally creates the graph. I want to actually show you this graph itself.
Um, so did you get the text?
Yeah, so I'm working on writing a prompt to get those signs. Yeah.
This is the graph that this particular text will generate. And if you can see over this graph, like since it has been built by BERT, so every single node actually has a 768 dimension vector attached to it, where it contains all of the information. Over here, sir, if you remember, around 30% of these, all of the nodes created were only valid. So these are the nodes that you gave in.
All the nodes. What did you say? What are the nodes created by?
Sir, Hauser sir has also sent you in the chat the nodes, and you can actually compare those nodes with the nodes that I am showing on the screen. And among
Yeah.
those, if you
So
could just
okay. So just
compare
one
and
second.
let me
So
know how many are
how's it?
correct.
You correct me if I'm wrong, Jose. So you actually cut and paste here the nodes which are created from LLM model, right?
Yeah, from ChatGPT directly. So I'm using
Oh,
the untuned, just a very general version of ChatGPT to generate such keywords extracted from the given text.
okay, keywords. So if I'm not wrong, they're almost same.
So like it's
Am
on
I
your
right?
screen, whatever you can see, and I just want you to again check which and how many are
Well,
correct. Because if sir
yes.
using a ChatGPT
So
version works to extract the nodes, it makes our works a million times easier. We can
say
directly use
again.
the API key and directly extract the nodes and then finally build these graphs.
I lost the two last three sentences. So what you're saying?
If the nodes that have been proposed by Houses sir in the chat, if all of these are
Uh-huh.
correct nodes from the text that
Mm-hmm.
I just sent, from the text that you had just sent me,
Mm-hmm.
if it
Mm-hmm.
is correct, then we can directly eliminate all of our pipeline and build a small direct way and use an API key to build all of these graphs within like a couple of minutes.
Yeah.
Our
Yes.
entire
So what?
model wouldn't have to, like, it's absolutely unnecessary to work that
Yeah.
hard.
So one thing is that also one of the challenge which actually Dave I also told you in the graph that we for I mean this is good graph for on the back end data we can keep it, but for visualization purpose
So
the graph
please
you want to
type in
see is
words.
only the nodes needs to be selected nodes which are coming from a dictionary. So like it has to be genes. So you see not all the nodes are genes here. There are only like a three or four nodes which are actually genes or the disease, and only those needs to be presented. So this is I think this is not a rocket science. It's very easy because the way I can provide you the files which are the like a correct nodes could be like what are the possible nodes and what are the possible genes. So once we have that, we can filter it out and then we can actually create the graph. Make it sense?
Sir, I'm actually telling something different. I'm telling just please
Uh-huh.
compare the nodes that have been created by uh, Houses sir and by my BERT uncased model, and please tell how many of those nodes are actually correct and need to stay in the graph.
Okay. So the thing is there are two things here. The models when they are creating a node, they are based on the text. Okay. There is nothing wrong that this should not be a kind of a node. It depends on like what how you are representing those text into kind of a into graphical sense. Makes sense, right? But what I am interested in the tool from application perspective, that all these nodes are not. I mean, even if it is a node just to build a relation on the from the text, but that is not what I want. So what I'm saying is not a right or wrong node. It is about what is right for me. Did you get that? What I'm saying? Because wild type tau proteins. Okay, this is a wild type tau protein. There is nothing like a wrong in the node. But basically, we do not have a wild type tau protein because there is already a tau gene is there, and we want to have just one node for that. So tau protein is there. Then tau, there is another node called tau. Now tau is actually another name for MAPT gene. Okay. So for me, I do not because in this way I will have like a thousands and thousands of nodes in my knowledge graph, and which will not make sense for me from visualization perspective. Again, I'm noticing that you can make a visualization any way you want it, right? I'm not saying it is wrong here. The graph which is showing here is wrong, or the keywords are wrong. These keywords are coming from the text, so there's nothing wrong. What the application we are developing is limited to only those genes and pathways and the disease. Otherwise, we will not be able to make any kind of an insight from those kind of a big graph. They could be in the database from the LLM perspective. That is fine. You know what I'm saying? So, because let's say when I'm asking a question and I want an answer that like similar to like ChatGPT AI agent, that can answer me based on the full knowledge graph. Okay, but when we are visualizing that data, did you get what I'm saying? Remember the tool which we are developing? In that tool, we only want to keep the pathway at right now it has only genes, but we can have like a genes pathway and disease in later in future. But right now we'll be focusing only on genes, relation between genes. Did you get that, Dave?
Yeah.
I mean, sir, I
Able?
don't.
Any comment?
So like,
Right.
I'm a little confused right now. Like, that, I mean, how do you want us to proceed right now? Using like the architecture that I proposed, or using just API keys and this open source models to extract keywords, relationships, everything? Because essentially, any model would do everything for you. Like
Mm-hmm.
when I mean it,
Okay.
like any
Yeah.
model, any open source LLM would do all the tasks that I mentioned to you. But the question comes, how accurate? How
Yeah.
accurate is that the open viral version of GPT or Llama, or how accurate is the fine-tuned version of BioBERT? Let's exclude LoRa for the time being. Let's how accurate is the fine-tuned version of BioBERT? So
Yeah.
I guess that
Actually,
is a decision that you need to take. Uh, I mean,
Yeah.
yeah.
Able.
again,
Right.
which,
Yeah.
yes,
Yeah. I just want to add that in the field of bioinformatics, I just published a paper on prompt engineering. Like we actually did some prompt engineering work to identify some for gene relation prediction specifically. And actually, in our research, uh, if the our we find that large language models can basically outperform uh, classic machine learning or deep learning models in classical text mining, res- like classical natural language processing work.
absolutely.
Actually, I mean, yeah. So why not? Why not large language model all the way and
So
get
when
the
I'm
result? It's probably too easy.
so throughout my presentation,
Yeah.
I have always used large language models. I'm just asking to use a better or a fine-tuned version of a large language models pertaining to a specific task. I never throughout
Yeah.
whatever I've been speaking, I never mentioned the usage of the libraries like Spacey or Word2Vec or even Glove 7b. Throughout, I've been using BERT, I've been using GPT, I've been using Llama, I've been using DistilBERT. I'm just asking to make a more fine-tuned version so that all of the data that we retrieve from these models, it is more accurate in comparison to what we would have received in other case of a non-fine-tuned model, which essentially comes again up to like the the trade-off between BioBERT and just pre-trained or the naturally trained GPT-4 or GPT 3.5, any you may take. That's
Yeah.
entirely my point, sir.
Yeah. I'm also curious. For, in our corpus, like when is the paper published? I think if the paper is published before BioBERT or GPT, because we know that BioBERT is a fine-tuned version of BERT, fine-tuned on PubMed articles. So if the corpus is not that new, BioBERT is probably already fine-tuned on it. Also, GPT, they have their training corpus is much larger, probably including archive, bioarchive, those publicly available data. So we can probably also presume that if the paper is not that new, uh, both BioBERT and GPT has seen the paper. So there is probably not that necessary to fine tune it again.
Sure. Then I guess what you're proposing is to just use BioBERT for our tasks, like a direct proposal that we had developed over here. Give BioBERT a query and directly ask it to build the knowledge graphs. Is this pipeline correct?
Yeah. So I think in my understanding, BERT is an encoding is an encoder, is an encoder only, and when you give it a query, the output, I mean the direct output of BERT is just vectors, right? A matrix of vectors, and we need to
Yeah.
like post process that matrix to get what we want. And I think this post processing is non-trivial to post process that matrix into a knowledge graph. What do you think?
I'm still, I guess I'm
So
having a miscommunication gap.
so,
So, like,
so I think
what
that
is it that you're proposing? Like, do we
so
give it something to other
so
than
let
BioBERT?
me I think Yibo, thanks for actually providing this insight because that was actually my main purpose behind setting up this collaborative meeting. That what I'm interested in an application where I can like develop a knowledge graph. Basically, it's a kind of a application for scientists to get a more precise knowledge or information about the question which I'm asking. So let's say, and the chat GPT is not sufficient for that thing. And in order to do that thing, one thing we want to know that let's say whenever there is an outcome, let's say that application is developed, and I ask a scientific question to that, and then it actually gives the chat GPT like output. It asks all this, also this, but I want to also make sure that all those answers coming from this application are actually sentences which are coming from certain paper. It is not like a made up of a story. That's the one thing. Second thing is that I want to take all those sources of all those publications and try to connect, see them into the network form so that I can overlay some other kind of bioinformatics data on that. So because this is just a kind of a network based on the literatures, but then I can have some, let's say, additional information data, compound data, or disease data, or differential expression data, or any kind of those databases. Then I want to map those. So it's more like a visualizing those network to make a certain outcome of that thing. So I want to have this kind of a application, which is a kind of a combination of these two things. It has a GPT-like response, and at the same time we can visualize a network where we can map the data more like from infographics way.
Okay, now I understand. So I think like the major output is actually the knowledge graph, right? Not the final response.
No, I
Yeah,
want
well,
the yeah,
yeah,
not binary file, but I want
yeah,
so the because one thing is that the GPT like outcome is very good. It's a very like a human like interaction. You can ask human like questions and it can answer you in a way so that you can understand it. Graph does not answer you, right? You
yeah,
can ask questions. Graph can simply highlight the things, but it cannot answer you in a human like kind of language, right? But the advantage of the graph is that there is a huge amount of data. It's like a protein-protein interaction data, right? You can see the network, you can identify the modules, and then I can find out, let's say if I have network, I can find out the disease modules. And from disease modules, I can identify the which pathways are enriched. And then I can go to those kind of pathway gene set enrichment analysis, GSEA. I can do that thing. So the lot of bioinformatics kind of analysis, which I want to do along with LLM like output. Do you know what I'm saying? A combination of
yeah,
these two.
yeah. So then I think what we need the most is probably the large language model agents to like highlight the graph. Also, probably, if possible, give the final response to the query. Right? And I think the gap for now is probably we don't have a very high quality knowledge graph, and that's what Dive is working on.
Yeah, so
Yes.
actually, the high quality knowledge graph. So I have another team of people who can actually provide the high quality knowledge graph data. They have actually knowledge graph data into Neo4j. They already created that. I can get that data. So, but this is just a data, which is like a build. I not. I mean, maybe next time I can set up a meeting and they can actually show you how the data is. So more like a structured data about the knowledge graph, which is created or generated based on not just the literature corpus but many other sources.
Okay,
Do you know what I'm
I
saying?
see. Yeah, I
Yeah.
see.
We can utilize the data. I'm right now actually, I think I showed you, right, that we are working with EGA on developing an application.
Hello.
And in future, not now, this is why actually this LLM based project which I started is a kind of an initiative, a new initiative. We want to develop a kind of application as an independent of the project with EGA. But in future, like I would like to see if this is something could be integrated as together.
Yeah, that sounds exciting.
Yeah. So yeah, so I think this is what we are interested. I'm interested to know further, and maybe we can find a better way solution to solve by working together. Do you think, Dave, Ibo?
Yeah,
I
sure.
think
I
Jose
mean,
is already on.
Sir, I would
yeah,
actually
I guess.
appreciate your insights into this. Like, I due to some reason or like communication gap, so I couldn't really understand like what you are proposing. So, like, are you proposing like this methodology that's on my screen right now, like this one? Like, is it this
Uh,
that you're saying that we need to give our query directly to the Llama or GPT and then it would give us the knowledge graphs, or is it something else that I couldn't get? Because I was reading the blog that you had sent, and even in there, like Rahul sir says ki you need to establish an RAG pipeline that would essentially give a specific set of prompts to Mistral 7 billion and Zephyr models in create the knowledge graphs accordingly. I again have this one knowledge graph as well for you. If I could share off my screen. Now this was built using GPT, a pre-version of GPT 3.5. I'll share off the full version of my screen so that I'm able to make sense actually. If you can see this file, I'm sure Gyan has seen it many times. Like this one is actually wherein I give GPT a Wikipedia page. This is like common sense question answering dataset. It is nothing fine tuned. We do not care about accuracy. We need to understand how GPT needs to find out. GPT finds out nodes and everything. So this how you want things to do? Because this was created using just one line of code and this is pretty simple to make. And I would be the like happiest if we can just work it off this way, because this was
Yeah.
like
I tried to extract knowledge graph from like hundreds of literatures using this way, and actually the first of course the result is not so good because uh, usually uh, specifically the recall is, the recall is good, but the precision is not that good, which means in most cases, just like what Dr. Srivastava mentioned, it will extract the same node multiple times and it will treat it as like different nodes. So it makes the knowledge graph looks very messy. Uh, but what I'm trying to propose is indeed doing it this way, because it's much simpler, and I'm mostly working on it from informatics point of view, and I think you are doing it more from a computer scientist point of view, right? You are trying to make it faster, make it efficient, evaluate all the possible solutions. And what I was trying to do is just find the easiest solution and get it to work. So what we did is, even though the knowledge graph extracted from those literatures is not good, but we can post-process those knowledge graphs. Like there are actually a lot of BERT variants, like BioBERT. If you know, there are also something like USMLE BERT, where you can use that embedding to merge those how to say duplicated nodes. And after merging, it's possible that we can treat that knowledge graph as like to treat those knowledge graphs as a perfect representation for those literatures, and we can use a large language model agent to query that knowledge graph.
How do you want to do this
Yeah,
backtesting? Like,
to
let's say
do
you're creating the knowledge graphs using the large language model, a complete untrained large language model. Let's say cloning it with an API key. How do you want to do this backtesting about verifying whether the particular knowledge graph has the correct nodes or not?
uh, I guess it will be very hard to like to directly verify that results.
So
I mean,
directly verify would
how do
actually
you?
mean like manually screening all of those knowledges, all of those graphs.
I
Because I've seen the
um
data that once Srivastava, when Gyan sir, when he provides them, it consists of around more than around like 1.5 million nodes. A graph encompassing that much amount of data is completely like impossible would be just a word, but it's very difficult to analyze all of those specific nodes and then decide as if which node is actually correct or not, if it were made
yeah.
through a process that comes directly without any fine tuning.
Yeah, I guess that's the problem with text mining. I mean, how do you plan to like to validate your methodology?
See,
Like
that's why I presented my
I know
entire
you have
model. I don't plan to re-verify my knowledge graph. I plan to build
okay.
my knowledge graph by fine-tuning the model. Like what you are telling is, first build the knowledge graph using the standard LLMs locally available, and then like
Yeah,
like improvise on this built knowledge graph by verifying the nodes built if I have received it correctly.
yeah, that's exactly
Okay,
what I'm saying.
what I am doing is making these models, I'm fine tuning these models into creating the perfect knowledge graphs which have a higher level of accuracy of being of having the correct nodes than the ones that were built by a non fine tuned or a non pre trained LLM. This makes things different
Yeah,
because this has a higher accuracy of being correct and like specific nodes rather than the previous one. Like if I
yeah,
was
but
able
I
to
guess
like
that
make some sense using my hand signals, whatever.
yeah, I can understand the point, but then
The architecture
then
becomes difficult,
I
right?
mean, you are doing this with some probably some online training need to be implemented because new literatures are coming out every day, and we probably need to fine tune that model every day. Just and
That was essentially
if
why
we
I
do it in my way, we need to update the knowledge graph every day. So that's I mean,
sir, like
I guess
Gyan
there's
sir,
no
like if you
perfect
are
solution
online,
for
sir,
this.
could you just once share of Gyan sir or Bhupesh, anyone just share of that once, that entire graph wherein we have all the genes. Like Gyan sir could do it, or we have Bhupesh also, who is like
Say
our
again,
tech team
what the
over here.
question you're asking?
Sir,
Say
if you could
again.
just share of the screen or the nodes and their first order graphs. Gyan sir is also there, Bhupesh is also there, who is our tech team. So I mean our backend developer team. So if anyone could just share of that, it could have been much more easier, I
No,
guess, for
so
Yuboso to get
so
it.
you are saying that the all the genes, is that you are saying all the genes known?
No, no, the graph that you use to show using Neo4j, or the one that Bhupesh, or so just give me 1 second. I'll call up Bhupesh as well, and I'll just
He's here. I see
Yeah,
Bhupesh is there.
yeah.
I'm here. I'm just okay.
He was
So
mute.
Bhupi,
Yeah.
एक बार वो screen
I'll
share करियो
just
ना.
take few notes and like represent that graph. Just a minute.
Just once share your screen and present that graph once. It would be
Yeah,
much
yep.
more,
On it, on it.
I guess, understandable for both of us. What are we dealing with? The amount of data.
Uh, just a second. I'm getting some notes. Chain information.
Random एक बार 300 notes लगा के देख.
In
So
first order,
now one
even
thing
if
is that
you
in the
take uh,
so while
for
Bhupesh is working,
50 genes,
right?
you will get around more than 10,000 nodes.
Yeah, just share your screen while you do it, na.
No, that
Yeah,
will be too much.
just
Visualization will collapse. And
possibly.
also, yeah, at that point, so this the in this application you cannot solve all the problems, but we can be little smart in that way that it is not necessarily that we want to visualize the full graph, knowledge graph. Okay, now I'm using the word little knowledge graph and the graph, two different words. Knowledge graph could be like a very complex graph information which has every information about the biology of the disease. Okay, you can ask any question, it's like everything. The graph which we want to visualize could be just a small set of the content of the knowledge graph which is meaningful for visualization purpose. It's like just a kind of short version of that thing, very short version of that. Do you think, Dave, this makes sense, you both? Because
Yeah.
there is a reason at some point, because let's say if I'm a scientist, I have a question which I want to ask and I want to get a more insightful answer from the model. That means that model has a full information on the back end. It's like a full knowledge graph. It knows everything. Okay. But what I'm visualizing, because I have some additional type of data I want to map onto that,